Welcome. You are about to view a recorded talk of the Progress and Visions in Consciousness Science online seminar series. This series is organised jointly by the Association for Mathematical Consciousness Science, AMCS, the Mediterranean Society for Consciousness Science, and the Oxford Mathematics of Consciousness Network. While every session consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. Further information and details on how to join are available on our website.
I talked to you guys back in January of 2022, and so maybe I can just give a short summary of some things that I've been up to since then that might be considered relevant. Then I want to jump into talking about, well, kind of my emerging pictures of consciousness and trying to answer this question of what it's like to be a computer. So starting off with kind of what I've been up to and maybe some seeds for conversation we might have. Back in 2022, beginning of 2022, this thing that we call the ruliad was young, at least in its name. As you might know, back in 2020, made this big progress in understanding the fundamental theory of physics and realizing that we really can think of physics as being computational all the way down. And that led to my sort of being thrust into thinking about consciousness because of the realization that the physics we see depends on the nature of our characteristics as observers. And that was emphasized by this idea of the ruliad. The ruliad is this entangled limit of all possible computations. It's a unique, necessary object that once you have kind of the defining idea of computation, it has to be constructed in the way that it's constructed. And the kind of the realization that our experience of the world is a consequence of us sampling the ruliad from within the ruliad. We are part of the ruliad, but we are sampling the ruliad, and in that sampling, we are getting the experience that we get of the world. And the sort of the key observation that I'm really excited about, actually, is that the laws of physics that we perceive seem to be a consequence of the fact that we are observers of the kind that we are. So in particular, the two key assumptions about observers like us, one could imagine other kinds of observers, alien observers, we'll talk about that later, but observers like us seem to have a couple of really critical characteristics. One, that we are computationally bounded. There is much that can go on in the universe that we are unaware of. And this is something which we'll maybe talk about this a little bit more also. The second law of thermodynamics is a quintessential example of how that works out. All these gas molecules are bouncing around. They have all these reversible microscopic interactions and so on. Yet we perceive there to be irreversibility in the world. We perceive entropy to increase and so on. But we do that because we are computationally bounded. We can't trace all those molecules doing their individual things. We conclude that the second law is true because we're computationally bounded. That's a place where we can see that a feature of the laws of physics is a consequence of the fact that we are observers of the kind we are. If we were observers who were computationally unbounded, could individually look at individual molecules and so on, people would tell us about, oh, did you know there was this thing called the second law? And we'd be really surprised because that would not be our experience. By the way, that same kind of thing happens with things like space and time. The fact that we perceive there to be a thing like space is a consequence, well, of a couple of things. One of the things it's a consequence of is the timescales on which things like our brains operate. You know, we look around us, we see, you know, a few tens of meters around us. The speed of light is fast enough that light comes to us from tens of meters away in a time that's very short compared to our brain processing time. So to us, we perceive there to be sort of instantaneous states of space at progressive moments of time. If we were much bigger than we are, or our brains worked much faster than they do, we wouldn't perceive that. If we replaced our brains with digital electronics that runs 1,000,000 times faster, we would probably not believe in space as being a thing that exists at a moment in time and so on. So that's another place. But the two key features of observers like us seem to be that we are computationally bounded and that we believe that we have a single thread of it, that we're persistent in time and we experience the world through a sort of single thread of experience. And so the really exciting thing to me is that those two features of observers like us seem to necessarily imply that we must observe physics to work the way that physics works, in the sense that the three big theories of 20th century physics, statistical mechanics, the second law of thermodynamics, general relativity, theory of space-time, and quantum mechanics, all three of those theories appear to be derivable from the assumption that we are observers like we are, so to speak, with those two characteristics. I mean, to me, this is a sort of philosophically, metaphysically, scientifically, really spectacular thing, because we'd never imagined that we could derive something like general relativity or quantum mechanics. Second law of thermodynamics, people kind of thought maybe might be derivable from something lower level. But the idea that all three of these theories, and they all work kind of the same way, are derivable from knowing sort of the computational foundations, knowing this idea of the ruliad, which is a kind of a necessary object, plus knowing the special feature of observers like us. That's been a big excitement for me in the last couple of years, is understanding that point, and we'll talk about that a little bit more later. One thing about the ruliad, this entangled limit of all possible computations, is it is the underpinning not only for physics, but also for mathematics. We can think of, we can start imagining kind of sort of patterns of theorems and so on that, and we can think about proofs as paths that go from theorem to theorem and things like this. We can start kind of constructing, we can start looking at what is metamathematical space like. Metamathematical space is the space in which theorems are embedded. And we can ask, what is the structure of metamathematical space? We can even do sort of empirical metamathematics, where we try and look at, these are sort of pieces of metamathematical space. I think I have a nice picture that's Euclid there. We have a picture, well, that's for example, the derivation of the Pythagorean theorem from sort of underlying axioms of set theory, the kind of outline of it. But you can kind of get a sense of where do, for example, notable theorems, here we go, where do sort of notable theorems of mathematics lie in this metamathematical space? In any case, the point is that this idea of sort of metamathematical space is the structure of all of these theorems that can be derived from each other, that entail each other, and so on. That structure is part of the ruliad. And so what we realize is that physics is kind of a slicing of the ruliad by physical observers like us. The claim is that mathematics is just another slicing of that same object, that same ruliad object, but by mathematical observers who have somewhat different characteristics from physical observers, though they necessarily share some common features just because of the way that we are. For example, mathematical observers share the feature of being computationally bounded. In mathematics, it's less important. The notion of progression through time is less important. And what instead seems to happen is that the mathematical observer just sort of has a bag of theorems that they think are true, and they're gradually adding more things to the bag of theorems that they think are true. But for example, the sort of, well, a key fact of physics is that it's, I'm jumping around a bit here, but when we think of something like the gas laws, we say, oh, we don't have to think about all those individual molecules bouncing around. We can just think about the aggregate of all of them and the aggregate features of a gas. So similarly, we can think about in space-time, we think in our model of physics that the underlying space is this giant hypergraph structure, but we don't perceive that. We perceive it to a good approximation continuum space because we're observers who don't get to see all those details of this sort of computational details of the underlying structure. So for mathematics, the same kind of thing happens. At the very lowest level, we can think of every little axiomatic piece of mathematics. But a working mathematician doesn't usually think in those terms. Like I showed you that picture of the derivation of the Pythagorean theorem. It's a big, complicated thing. But the fact is that most of the time, when you think about the Pythagorean theorem in mathematics, you don't have to say, oh, and by the way, I've defined the real numbers in exactly this way, and this is what's happening at this deeply axiomatic level. Rather, you can say, I believe in the Pythagorean theorem. I can go and prove other things from the Pythagorean theorem. In other words, much like the gas laws for molecular dynamics or the concept of continuum space for space-time, we humans sort of perceive things at a higher level than sort of the underlying elements that are making the thing up. And so it is, I think, with mathematics. The big fact about mathematics is that higher level mathematics is possible, that we can just talk about the Pythagorean theorem and deduce things from it, and we don't always have to sort of grind our way down to the very lowest level axioms to talk about things. So that's I think the in a sense the fact that higher level mathematics is possible, I think, comes from the same place in a sense that makes us believe in continuum space, or that makes us believe in fluids rather than just discrete molecules and so on. So in any case, this is so I was working on metamathematics and trying to understand sort of the physicalization of metamathematics. There are a whole bunch of other things here that I could talk about, but I want to one of the things I even wrote a book about the second law of thermodynamics. A thing which Lenore had shown my early reports of my work, so to speak, from when I was 8 years old. I happened to start working on the second law of thermodynamics when I was 12 years old, and I was pretty happy that finally, now, last year, I think I actually feel like I really understand the second law of thermodynamics. And it comes out of this whole story of observers and how observers work and so on. Well, then another thing kind of came on the scene, which was ChatGPT. And we've been deeply involved with the ChatGPT and LLM world because our computational language is kind of the complementary strand to thinking about things in the way that AIs and LLMs think about things. What we're trying to do with our computational language, with Wolfram language, is to find sort of this precise computational representation of the world from which you can kind of build sort of solid bricks of consequences and so on. So, but in any case, that led me to write this thing about what ChatGPT is doing and why does it work. It's kind of frustrating to me because I wrote this little tiny book that about this, which has been, I think, my most read document ever, which is a little frustrating because I wrote it in like 10 days, and I consider it one of the more trivial things I've written. But it's perhaps relevant. It'll be relevant to what we're talking about here, because one of the things that I really worked on quite a bit is, why does ChatGPT work? You know, we can understand that it's just sort of one word at a time, figuring out what's the most likely next word. You know, it's sampled the web and other things, and at the simplest level, it's saying, you know, if the prefix is the cat sat on the, it's just asking, well, what, according to the text it's read, the trillion words it's read, what is the most likely next word statistically? But that's obviously not enough, because there are many things you might prompt it with that it will never explicitly have seen. So what's important is that it's making a model of what might be the next word, and that model is a neural net. And the thing which is not obvious, but seems to be true, is that a model made with a neural net seems to more or less agree in the way that it extrapolates things with the way that our human brains extrapolate things. And most likely the reason for that is because our human brains are neural nets. And we might have wondered before ChatGPT and so on, we might have said, well, there's something in brains that we can't quite get our hands on physically and so on. There's something mysterious going on deep inside brains. And we might give evidence of that. Oh, look, you know, human brains can produce talking and language and all this kind of thing. And that's really hard. Well, the surprise is that with just a simple neural net, you can do a pretty good job of producing sort of flowing essays and things like this. And the thing that and that's the fact that you could have said, well, it's just copying what's already there on the web, but it isn't, because there isn't enough sort of statistical power in what's there on the web to be able to write the next words, so to speak, in all cases. You have to have a model. And, I was mentioning in sort of the pre-mention here that in the end, one of the things that comes up in science quite often is people say, we finally invented a modelless model. We finally got something that's going to be able to figure out what's going on and extrapolate things. And people sometimes say brains do this, that brains are a modelless model of the world, that they can figure out what's going to happen, that they can figure things out, but that they're not relying on their internal essential features to do that. But in fact, I think the fact that it's possible to get that you kind of extrapolate language in the way that a neural net can extrapolate language the same kind of a way that we extrapolate language is a consequence of the fact that we really operate in the same kind of a way that a neural net operates. Now, one of the things about ChatGPT that one can ask is, so is it, what's it really telling one about language and how language works? And is it in fact the case that the very fact that ChatGPT works is a sign that there are regularities in language that we didn't already know were there? And I think the answer to that is yes, that we knew about language, that there was a syntactic grammar of language, that we put together language by saying that there'll be nouns, verbs, nouns, things like this. But what we haven't known is that there is also a kind of semantic grammar of language. There is a kind of a construction kit of the way that we can put together language to make it be plausibly meaningful. The one example of that we have is logic, where, in my view of sort of a model of Aristotle, so to speak, is, he took a bunch of examples of rhetoric and he did machine learning to figure out what were the patterns that you could abstract from that turned into syllogistic logic. So, we have that one example, but I think what ChatGPT kind of shows us is that there is sort of a further construction kit to language that we didn't already know. But in any case, but I think the other meta point for purposes of consciousness and so on that I think is really important is that yet another thing that we thought we might have to seek something outside of the mere computational, the merely physical or something, for brains to explain how a thing like this, like writing essays, works. We now realize we don't really have to do that. So in any case, something that I'm just going to mention another thing that sort of came up about generative AI that I think is also relevant to the things we're talking about here. I just want to set some more context, so to speak, is this has to do with the question of, well, I've really been interested in this question of alien minds and how can you get inside an alien mind, so to speak? How can you think like an alien mind? And so here's an example where Laura's asking, am I bringing Chomsky back into ideas of language generation? I'm pretty sure that Chomsky thinks that he totally disagrees with me, but I don't know if that's really the case. I haven't talked to him recently. I think he's written some stuff about things I've written, so maybe there's a indirect. But I think one of the things that, in my view, is crazy, that has been a thing in linguistics for a long time, is meaning doesn't matter. All that you have to talk about in language is the construction, the syntax of the kind of the constructional syntax of language. I think that's completely missing the point. I mean, I think that the important point, language, here's my view of language. We have certain internal thoughts going on in our brains. We all have different detailed neuron firings that represent those thoughts. The question is, how do we get to communicate those thoughts to somebody else? who has a different pattern of neuron firings. Somehow we have to package those thoughts in a way that is transportable. And that packaging, I think, is language. And for example, some elaborate pattern of neuron firings that to me represents a cat, I have to package that up into the cat concept and the cat word that I can then say, and you'll unpack it and produce your collection of neuron firings that are your representation of a cat. And so I think the essence of the sort of the thing language achieves is this way of communicating, being able to package up thoughts so that they are communicable. Now, an important feature of language is that it's kind of compositional. We have this idea that we don't just have to, if all we had was nouns, we just point at things and say, chair, table, whatever it is. But language does something more than that. It has this kind of modular, factorable character to it that is an important feature. Our human language tends to be one-dimensional. That's not a necessary feature of language. It's probably a feature of the way that brains work. It's certainly a feature of the way that LLMs have been constructed with transformers and things like this. But in any case, by the way, to talk about this idea of concepts, I think, okay, so now going deep in the rabbit hole here, this concept of the ruliad, this entangled limit of all possible computations, you can say that you have all these computations, they're running, they're progressing through time. You can say, well, let's take a slice through all of those possible computations. We have a kind of a moment of time across all of what we call rulial space. And we can think of these different places in rulial space as corresponding to different kind of points of view about the rules by which the universe is operating. Alternatively, we can say we take a slice through the ruliad, every little piece corresponds to, a different Turing machine that we attribute to being the rule for the universe. And when we move across the ruliad, when we kind of try and translate across the ruliad, we can do that by essentially saying we are going from one universal computer to another by applying some transformation that is some compiler or interpreter that goes from one universal computer to a different one. So, but there's a question, which is, when you're looking at space, whether it's rulial space or physical space, there's a question of, is pure motion possible? So you might say, well, it's obvious that you can just take something and move it around. That's not obvious at all, I think, because if you think that that everything is made of something lower level, for example, you think that we're all made of atoms of space in some giant network. As we move, we're going to be made of different atoms of space. So the fact that there's the same us at a different place in space is non-trivial. We are reconstructing ourselves effectively at a different place in space. I mean, the analogy here is in a fluid, for example, you can have a little eddy that's made of a bunch of molecules going in a circle, and that eddy can move around. The individual molecules that make up the eddy can be quite different over time, but yet there is some kind of existence to this eddy that can sort of move without change. In physical space, our everyday experience is that things can move without change. In general relativity, that's much less obvious. If you're near a space-time singularity, you have an object, the object will be torn apart as it goes near the space-time singularity. You can't expect pure motion to work near a space-time singularity. In our models of physics, where there is an underlying stuff to space, it is a non-trivial claim that there can be things that move around, like the eddy in the fluid, that move around in space, being reconstructed with different atoms of space at every moment in time and still maintain their integrity, so to speak. That's a thing that you in effect have to derive. It's not something that comes for free. But the key type of thing in physical space that has this feature that it can propagate without change is a particle, like an electron, for example. A feature of a particle is that it is a thing that maintains its integrity as it moves through space. So what's interesting about that is when we think about rulial space, we can ask the same question. What is it that maintains its integrity through rulial space? And I think the answer is it's concepts. In other words, at two different Turing machines or different brains, a concept will be encoded in quite different ways. But the question is, can you package up a robust thing that can be essentially moved through rulial space and arrive at another mind, so to speak, and end up being sort of successfully unpacked? And so I think there's this kind of bizarre analogy between particles in physics and concepts in rulial space and so on. But in any case, the idea that language is possible is the idea that it's possible to do this kind of packaging. It's possible to translate things from one mind to another in such a way that they can be readily unpacked by the other mind. And I think that's a thing which one can imagine actually deriving that should be possible. It's not self-evident that will be possible. It could be that every separate mind just has its completely different view of the universe, and there's no way to communicate between them. So in any case, I was just going to mention this kind of exploration of alien minds. So kind of the idea here is, I probably have some better pictures of this, but I'll just go through here. This is let's see, you tell a generative AI to make a picture of a cat in a party hat, and it's seen 5 billion images from the web, and it's seen the image and a caption for the image. So when you say make a picture of a cat in a party hat, it is going to basically go from the images it's already seen and figure out how to effectively interpolate between those images to eventually produce the picture that you requested. Okay, but when you do this, inside this process of defining what picture you want, you've made an embedding space. You've made a description of the picture you want that is just a vector of numbers. And we could talk about how that in detail works. But the main point is we've taken those English words and we've just turned them into some vector of numbers that represent the concept of a cat in a party hat. So given that we have that vector of numbers, we have a notion of sort of a space that we can move around in. So we can kind of move from the vector of numbers that represents a dog to the vector of numbers that represents a cat. And we can see the kind of dog-cat transition happening here. But we can also go and we can say, let's look around the space of that, in this space of kind of concept space, so to speak, around the concept of a cat in a party hat, and look at what's nearby. And what we get is what I was calling Cat Island, which is this region of the space of possible concepts that corresponds to what we think of as a cat. But as we go away from that, we get into what I've called interconcept space, and analogous to interstellar space, something which is away from our known concept of a cat. It's this thing that lies between our known concepts. So one thing that's a little bit sobering is you can try and work out what fraction of interconcept space actually has concepts that we humans have invented so far. And the answer, even in this very coarse approximation, is maybe 1 part in 10 to the 600. So the vast majority of interconcept space is full of concepts that we humans have not yet made up words for or decided were important to us. And it's kind of a way of understanding this ruliad object. This is sort of a way of seeing what's out there in the ruliad, away from the parts that we have already colonized and given names to and so on. So in any case, one can also study the question of when there is a this is a mind that has been sort of aligned with human minds. It's a neural net that's been trained from actual images on the web and so on. You can ask the question, what happens? It will generate all sorts of things in interconcept space. You can ask what happens if you just take that mind and you change it. So instead of having the neural net that was trained from the actual images produced by humans, you say, let me take that neural net and let me start modifying it. It's kind of like experiments you might do in neuroscience, where you zap a part of the brain and you see what does the brain do when you've zapped a part of the brain. Well, we can do that with artificial neural nets much easier than with brains that we can talk to, so to speak. And what we find is that what we get are these sort of, this is looking at different, the kind of bizarre images that are what you get by zapping different pieces of the artificial neural net. Sometimes it's a distinctly cat-like thing. Sometimes it just produces something that is very uncat-like. Sometimes it's a kind of a rather more lonely cat, and so on. And you can really, it's sort of a great lab for understanding what an alien mind might do, so to speak, because these are minds that are very close to human-like minds, but they've been made slightly alien because you've changed the weights of the neural nets to just modify them so that this is what the modified neural net thinks is a cat in a party hat, but it's not what looks like a cat in a party hat to us. And you can do things, all sorts of terrible things happen. You can actually, one thing you can do is you can just start sort of amping up the amplification in the neural net, and you essentially blow the mind of the neural net, and it produces all kinds of strange sort of psychedelic-like things as it gets blown up like that. You can also do things like this is kind of a HAL-like experiment. Oh, I think that maybe one down here is the where you just switch off successive parts of the brain, and eventually it will kind of go to blank. In any case, so those are some things I've been up to. I think the biggest thing that I was looking at recently that perhaps is of interest to people here is this thing I call observer theory. But let me return to my original topic, which is what's it like to be a computer? So I was hoping to have written something about this, but I haven't gotten it finished. I suppose one thing I could say to begin the process of thinking about what it's like to be a computer is to think about what it's like to be a human as viewed from the outside. You know, I happen to, because I'm a kind of crazy informational pack rat, I get all kinds of data. I've been recording every keystroke I type for 25 years now, but I also try and measure all kinds of things about myself. And I recently did some whole body MRI. And so you can, there's the brain that you're talking to right now. And that's one view of it. I think I had some other views of, that's the brain that's talking to you right now. It's very physicalized. It's kind of, to me, it's very striking that you can just, here's this thing, and it's very clearly a physical thing. One thing that I might sort of offer to you as a question, let's say, we've had this whole discussion, I'm going yakety yak, and I seem to be very human and so on. But let's just imagine that I showed you this MRI, and instead of there being a brain in a large part of this MRI, there was a piece of digital electronics here. Let's imagine that that was the case. But you've been having a discussion with me, and I seem pretty human. But yet, what if there was actually a big lump of digital electronics here? What would you then think? Would you then say, whoops, I've been fooled. This isn't really a human I'm talking to. This is something different. What would you think about that? It's funny because for me in particular, I happen to have sort of exposed a lot of stuff that I've done. So I do lots of live streams and things like that. But the end result of this is there's 50 million words that I have produced that are out there available on the web, which is a fair number. And one question is, from those 50 million words, how much of me can you reconstruct? So somebody recently, for example, made this thing they call Stephen Bot, which is trained from, I don't know, about 15 million, I think, words of mine. And you can, I don't know, you can try it. Let's see what happens. I haven't tried anything like this, but let's see what it does if we say that. What's it do? That's boring. It's probably going to. I don't know. Can you hear that? Did you? It was talking in my voice.
Heard it very vaguely, but wasn't able to hear the details.
Okay, let's see if I can set this to share sound. Here we go. Let's try this again. This seems like a very boring answer, but let's. I think I should do better than this.
what characterizes consciousness is the ability to recognize patterns in the world around us, enabling us to form coherent models of our environment and our interactions within it.
Blah, blah, blah. Anyway, I thought it was fun. I didn't make this myself. But it's sort of an interesting thing that given, to what extent can you extrapolate from 50 million words to get a thing that will behave a bit like this thing behaves? But let's talk about computer for a second. Let's, the sort of a question would be, what is, here's the view of sort of what it's like to be a computer. And I tried to trace this through for a traditional computer, forget AI and all those kinds of things, just your average laptop, okay? The first thing to realize is it is the time from starting it up to the time when the operating system crashes. That's like a human life. Because during that time, the computer has started from a certain set of kind of genetic characteristics. It maybe even knows a certain amount that was left on its hard disk from the last experiences that it had. Those are the kind of books it's reading and things like this. But then it builds up a certain amount of memory of its life until it crashes, it's restarted, it loses that memory, the next generation starts up, so to speak, and it has its next level of experience. But during that time, from startup, from boot to crash, that's kind of like the span of a human life. And you can start asking, well, what is the experience of the computer? What does it, for example, does it conclude that that other things around it are like it? So one feature of us humans is, we have our own internal experience, but one of the key things we do is to assume that other people have similar experiences to us. That's sort of a foundational assumption about entities like us. If we didn't, right now, when we look at a computer or an AI, we say that thing, oh, that's obviously not like us. I have to say, I think by the time so there's this, for the computer, there's also this question about sort of, are there other things out there in the world that are like it, like other computers, for example? And what you realize is that the computer, like us, has the same kind of language communication experience that we have. That is, a computer has a certain configuration of bits in its memory, and every computer running, every time it runs, even if it's two identical computers, it will end up with a different configuration of bits in its memory, representing running the same programs, representing the same thing, depending on detailed timings of memory allocation, all this kind of thing. It will end up with a different configuration of bits in its memory. And so, for example, just like with humans, we wouldn't expect that if you were to take the kind of neural engram of one of us and just inject it into another of us, we wouldn't expect that the thoughts the first person had would be transmitted to the second person. We don't expect there is direct memory copying from one human to another, because we expect that we've all encoded our thoughts in a different way. And so it is with computers. And so how do computers communicate? Well, they do the same thing we do. They package things up in some protocol, language, Ethernet packets, whatever it is, to communicate to another computer. And then at the other end, that language, that communication channel is unpacked, and it becomes something that now goes into the internal memory of that other computer. And then you can ask questions like, well, does the computer think that it has free will? That might be a reasonable question. We think we have free will. Actually, the assumption of free will is one of the things that we kind of assume about ourselves as observers within this ruliad and so on. For example, free will is what gives us the idea that we can do any experiment, or that we can, that we can make a choice. We're doing quantum mechanics. We can choose to move this polarizer to a 30-degree angle or something, or to a 60-degree angle, and that it isn't just predetermined what angle we'll move it to. That we have this assumption of free will that's fairly fundamental to our view of constructing our view of the world, so to speak. So as a question, would a computer think that it has free will? Well, I think that the question, to me, one of the key ingredients of free will is it's not obvious what you're going to do. If it's obvious what you're going to do, it doesn't. It is not the case that your will is determined by something. It is not free. It is something that is sort of visibly determined. But one of the phenomena that's sort of a key thing that I've sort of talked about in science for a long time is this phenomenon of computational irreducibility, that even when you know the rules for a system, to work out what the system does, you may just have to follow through each step and see what the system does. That's sort of a tighter version of what we've known forever and ever about universal computation and undecidability and things like this. But when you have a system that has computational irreducibility, it means that there isn't a way to jump ahead and say, oh, I know what that system is going to do. You have to follow each step and just see what it does. And so I think that to me is sort of an essence of the phenomenon of free will, is that you can't know what's going to happen. If you can always say, oh, I know what you're going to do, then it's very obvious you don't have free will, because you can see that the moth is going to go and keep bashing itself against the light. You can say, I know the neural circuit that makes it do that. You can kind of readily identify that you can know what it's going to do. It seems to be a determined thing, not a free thing. Well, I think that this phenomenon that even there's, even with a simple computational rule, you can get behavior that you cannot predict except by running through each step. That phenomenon of computational irreducibility, I think, to me, is sort of the essence of what makes us feel like we have free will. It's also core to many other things. For example, it's core to the concept of the passage of time. It's the fact that there is something happens as time progresses, is because there is a computation that is being done, that is being progressively done through time. And that's why the passage of time is meaningful, is because we can't just jump ahead and say, we can just jump to the end and say what's going to happen. We have to follow each step. We have to actually live through the passage of time, so to speak. I mean, there are a very large number of other consequences of computational irreducibility. I would say that one thing to say about computational irreducibility is sort of a perhaps interesting sort of history of science, philosophy of science point, which is kind of the thing that's been a feature of science for the last 300 years or so, is this surprise fact that kind of it started with Copernicus and so on, like, don't trust your senses, just trust the science. We can use math to figure out how the world works. And that turned into kind of, we can, given the world as it is, we can just use math to immediately say this is how things are going to work in the world. And we can kind of we can immediately sort of jump to the end and say what will happen, so to speak. Well, what computational irreducibility is doing is effectively saying that from within science, you learn a major limitation of science, that there are cases where you can't expect to just sort of jump ahead and know what's going to happen, that you have to kind of follow through each step and see what happens. But in any case, from the point of view of kind of the computer and how it feels about itself, I would claim that I would claim that to the computer, it has the same perception of free will. It can look at another computer and it can say, I don't know what this other computer is going to do. I have to follow through each step and see what it's going to do. Or for itself, it can say, it can't say, oh, I've got this formula that tells me what I'm going to do in every case. It has to actually live through those steps to find out what it does, rather than just saying, I know I've got some little formula that I can pull out of my back pocket and say, this is what I'm going to do in this case. And so it has that same sort of experience of that. Now, I suppose the question is, when it comes to what is, you would like to know what is its essential internal experience of things. And for example, how does it experience the world? For example, I've said that the way that our laws of physics are is a consequence of the way we are as observers. And we have these features like computational boundedness and so on. We perceive the world to have the laws it has because we are observers of the kind we are. And so then you can ask the question, well, as a computer, how do you perceive the world? And some aspects of how computers perceive the world are very much like ours. There are some differences, however. For example, computers run 1 million times faster than we do. Their cycle time is in the gigahertz range. The frequency is in the gigahertz range. Ours is in the millisecond type range. So, theirs is nanoseconds, ours is milliseconds. So, for example, this question I was mentioning about sort of the perception of space, not obviously the same for a computer. It's not obvious that the idea of space would be something that, the fact that we perceive the world to be the way we perceive it to be is not completely unrelated to things about our size, our physical size, our temporal size, and so on. If we were, if we look at how big we are relative to the universe, we are roughly 10 to the minus, in linear dimensions, we're roughly 1 10 to the 26th of the distance across the universe. Probably relative to the atoms of space, we may be 10 to the 100 times larger than distances between atoms of space. So we are, in a sense, quite big on the general scale of things that can exist in the universe. But the fact that we perceive the universe the way we do is not unrelated to that physical size that we have. That and for a computer, for example, it's the time scales and so on are somewhat different. And it's an interesting question. You can start asking, what would the world be like if you perceived things 1 million times faster than we do? And I think that, for example, as I say, light, the propagation of light becomes a significant thing. And just like the propagation of sound is something that we have some perception of, though not very much, we would have a lot of perception of the propagation of light, and this idea that there is a visual scene that we can construct that is this all-at-once visual scene would no longer be there. But so in any case, I think people, I think the last time I gave one of these talks to you guys, somebody raised this question about the concept of red and the idea that surely there is no inner concept of red to a thing like a computer. And I really don't think that's right. I think that there's no less an inner concept of red to a computer as there is to sort of the neural nets that make up our brains. I think that the sort of the shocking thing, in a sense, is that our internal perception of things going on is really just kind of our experience of a set of processes that are sort of deeply physical or computational, so to speak. And there's sort of this question of, can we, the fact that, well, for example, the fact that we can derive things about how the world has to appear to us from the way that we imagine that we are as observers, I think is sort of a significant piece of this picture. I should say something perhaps about this whole kind of notion of observers. What is an observer? I've tried to understand sort of a formal definition of what an observer is. When we think about computation, we think about, we have a set of rules, we progress according to these rules, we keep applying these rules. That's what a computation does, is it kind of creates fresh stuff based through time, for example. As the steps of the computation progress, you get sort of fresh stuff being produced. What does an observer do? I think what an observer mainly does is it takes the complexity of the world and it somehow manages to stuff it into a finite mind. How does it do that? Well, it takes some sample of the world and it somehow simplifies what it perceives of the world. Even though there's all this complicated stuff going on in the world, what actually ends up in our brains, in our minds, is something much simpler than that. How do we do that? The fundamental thing that we're doing is we're equivalencing many different possible states of the world. And we're saying what we care about is just the equivalence class of states of the world. So, for example, if we are looking at, some visual scene, I'm looking at this display here. I am perceiving from that display only certain overall features. The individual photons coming from that display, the individual pixels even, are things that I am many different configurations of photons or pixels or whatever, I would consider to be just the same as far as my perception is concerned. And what we see across all forms of perception, I think, and all forms of measurement is the same kind of thing. You know, if you look at different kinds of ways to measure things, I think there are about 10,000 physical units that people talk about. We've had to catalog them for Wolfram Alpha and so on. And they're all kinds of different things. But if you say, how are all those things measured? Turns out that it's the same pattern in all cases. There are many details, but the measurement is some aggregated equivalenced thing that's sort of a much reduced description of what's going on. So for example, here's an example. If you take something like a pressure measuring device, you have a bunch of molecules in a gas, and you have a piston, and the piston is measuring pressure because it's being pushed by the molecules in the gas. But there are many different configurations of molecules in the gas, all kinds of different ways the molecules can hit the piston. But as far as the piston is concerned, all that matters is the aggregate force exerted by those molecules hitting it. It is equivalencing all those different detailed kind of configurations of molecules and getting out just this one kind of result of what the pressure is. And that seems to be what is sort of universally happening in different forms of perception and measurement and so on. I mean, we humans have certain built-in senses, you know, vision, hearing, all those kinds of things. We've extended our senses somewhat through technology. We've not perhaps been as imaginative as we could be in building sensor devices. Those sensor devices are still very much based on the senses that we already know we have. If there was some other kind of thing in the world that we just have no awareness of, we probably wouldn't have built a sensor for it, just because those aren't things that would be deduced from our intrinsic experience of the world based on the senses that we have sort of biologically evolved. But in any case, so I think this idea of equivalencing, this is the core notion of what it means to be an observer, that you are making all this equivalencing to be able to, and we talk again about sort of the computational boundedness of observers, to be able to stuff all that complexity of the world into the finite mind. Now, it's sort of interesting to realize that if we imagine lots of different sort of threads of history, that computation is extending those threads of history. Measurement, observation, and observer is equivalencing those threads of history, is pushing them together. And so there's two sort of transverse operations that are going on. The process of evolving computationally and the process of observing and equivalencing is kind of the transverse reduction of that. And so it is, as we look at the structure of the ruliad and so on, we can see that quite explicitly. We can see, oh, we're actually taking patches in space where there are many different sort of threads of causality, and we're smushing them all together to make our sort of finite mind observation. I should say, by the way, that when you start looking at all these different measuring devices, and I've looked at a bunch of them, but I think it's a good exercise to look at even more, that a very, very common story is this aggregation process, like in the piston. But what's really happening in that case is sort of interesting. You know, as each molecule hits the piston, there'll be some sound wave produced in the piston. The piston will wiggle around. It's that the time scale for sound to propagate in a solid piston is very short compared to the time scale associated with sort of motions of molecules in the gas and so on. And so that's why you can reasonably talk about it as being a sort of single aggregated effect. And that's a very typical case, is that you're basically taking averages like that. There's one other class of measurements that are important, which is what happens with something like a weighing balance. In a weighing balance, you're sort of putting things on one side, putting things on the other side, and eventually, clunk, it goes one way or the other. It makes a definitive decision. This is heavier, that's heavier. That is again an aggregation. It's the same kind of story of equivalencing. It doesn't matter what the sequence of weights you put on one side were. All that matters is their aggregate weight. And I think the weighing balance story is much more similar to typical qubit measurements, for example, in quantum mechanics. And it's again the same type of thing, but it's a measurement where there is a definitive, it's this versus that, rather than it's this sort of average quantity. It's a little bit confusing as you start thinking about this in the context of quantum mechanics, how that works, but that helps, I think, clarify that. I mean, I should say that I didn't talk about quantum mechanics, but I should say that in our models of physics, there's this notion of these multi-way graphs that represent sort of all possible histories of the universe branching and merging and so on. And one of the key observations is that just as we are extended observers in physical space, aggregating over a large chunk of atoms of space, so we are also extended observers in what we call branchial space, in the space of possible histories of the universe. So in a sense, quantum mechanics becomes this story of how a branching observer perceives a branching universe. And it's the very fact that we are sort of aggregating over this region of branchial space that leads us to believe that, for example, definite things happen in quantum mechanics.